my pleasure to. Okay. Good afternoon, everyone. Yeah, so it's my pleasure to welcome Stefanie Mueller to this UCLIC seminar series. So Stefanie is assistant professor in MIT ECS department, and she heads the HCI engineering group at CSAIL. I had the pleasure of visiting her group 2 years ago when Mariana and myself spent the summer in her team as she was setting it up. It's an amazing group. They're working on personal fabrication and all kinds of 3D printing and programmable digital data, which is what she's going to talk about. I've known Stefanie now for over a decade. When she, in fact, I think we first met when she was starting out her PhD, it's really interesting to see her how she's been doing over the last 10 years, paper after paper at Chi and WIST, and as she notes, she's received so many best paper and honorable mentions that even she's probably losing count.
But very kind of you.
But yeah, so it's a pleasure for me to welcome Stefanie, and I'm looking forward to your talk.
Yeah, thank you so much, Shri, for the introduction. Obviously, I hope to have you and Mariana and some of the other folks back sometime when all of this is over. One thing I forgot to ask, can you remind me of what the timing goal is? So the talk should end 10:30?
So it's like 40 minutes for the talk plus 10 minutes for questions.
Okay, sounds good. Okay, perfect. All right, thanks so much everybody for coming. I'm really excited to see you all here in such great numbers for the talk. So I'm really excited to show you my recent work on advancing personal fabrication, and we had a special focus in the last years on making physical objects as reprogrammable as digital data, and I will show you a bit more about this in a second. So computing has really revolutionized how we process and interact with digital data today. And I'm sure everybody has their own personal example how computing over the last decades has changed how they work today. For me, since I work in 3D printing a lot, I will choose the example of 3D modeling here. So if you imagine how people did product design, let's say 30, 40 years ago, they would probably sit down and they would use paper and a pen and they would make a sketch of, for instance, a car. And then if they had to make changes, they would basically have to resketch everything. So this was a very tedious process. Now today, product design is so much easier because you can simply take a 3D editor, you make a 3D model, and then if you want to change the shape or you want to change the color of the 3D model, it's super easy. You just take a few clicks and you have the new object right for you on screen. So in digital, super easy these days. However, if you think about this, these awesome capabilities are not yet available for physical matter. So taking the example here of the car again, if you wanted to change the color of your car, for instance, that would be quite a laborious and time-intensive process and also very costly, right? So you would have to bring your car, for instance, to the store there, right? And they would recolor it, and it's just like, it's a big mess. So in my group, I've been asking myself, how can we actually enable it that physical objects can be as easily changed as we can manipulate digital data today? So in this example here, can we make it as easy that you just have a click and, for instance, the color of your car will change? So let me talk a bit about reprogrammable appearance to show you one of the first projects we had in this space. So we have 2 papers on this. If you're interested in more detail, you can look them up on our website. I will give you a brief overview now. So we developed this smart material that you can simply spray onto a 3D surface. And then you simply have to shine light from a normal office projector onto the object to be able to program its appearance and its color. So here's some examples of this. This is a phone case. So imagine on a daily basis, you could actually change, for instance, your products that you carry with you every day to, for instance, adjust your fashion. This is a shoe that can be reprogrammed. Maybe in the future, in the night, you put your shoe into a shoe box. Next morning, you have a different pair of shoes. And this is also a fun example here, a reprogrammable car. And you can imagine maybe a car sharing application where different users want to use the same car, but they still want to personalize it. So I just want to show you the images again. This is the phone case. Right now with our system takes around 20 to 40 minutes, depending on the texture you want to program. And again, it's the same phone case in all of these images. Here's the shoe. This is actually a collaboration we have with New Balance at the moment. So it's not so far away from maybe becoming a product in the future. And then this is the car. This is a collaboration we have with Ford Automotive at the moment. Again, just to see like what the future can hold in that area. We are also looking into textiles. So there's interesting questions on putting this, for instance, in normal clothing that you wear on your body, maybe, for instance, to increase sustainability and reduce waste. So I put this example here. A lot of us have like pretty similar clothing in different colors, right? Couldn't we have just like one piece of clothing of the same type and we can reprogram the appearance? And then this is an interesting collaboration we are looking out for right now. This is with Benjamin Moore. They are making wall paints. So could you, for instance, also paint your walls in your room, and then maybe when you leave your office, you program an appearance with an app and you come home and your living room looks completely different. Okay, so one question obviously is like, how does this actually work? And I will give you an overview of this right now. So underlying our smart material are these photochromic dyes. So by default, they are transparent, but if you shine some UV light on them, they become colored. Now you can use them in your normal environment. And then if you want to make them transparent again, you can shine light from an office projector and they switch back to transparent. So this process is repeatable. You can do it as many times as you want. So just for summarization here again, so saturation is with UV light, and then desaturation is with visible light, which comes from a normal office projector. So this was cool when we saw it for the first time, but the limitation here is it's really just a single color. So when you buy those materials from a company, you can get them in transparent to cyan or transparent to yellow or transparent to magenta, but it's just single color only. So we wouldn't be able to make these multicolor textures I showed you at the beginning. So how can we actually achieve multiple colors? So our idea was to get inspired from how normal color mixing works for inkjet printing, for instance. So you take the cyan, you take the magenta, and you take the yellow, you mix it all together, and you get a black ink. And that is very consistent with the CMY color model that you see on the right side. So how can we now actually control each color channel in the solution separately? So you have this one black bottle, but there's cyan inside, there's magenta inside, and there's yellow inside. So how can we activate and deactivate those individually in the single one material? Because if that was possible, we could actually do all of these different colors you see on the right side. So let's say if we deactivated the cyan in the bottle, the cyan would be transparent to the human eye, and you would only see magenta and yellow, and that would give you red, right, which you see in the second image. Let's say if you wanted to have green, you would have to find a way to make the magenta transparent, so your eye only sees the cyan and the yellow, which then gives the green bottle and so on. So how can we do this? And that's probably the most technical piece of this work here. You have to know a little bit about wavelengths of light and how the projector actually emits the light. So to break this down here for you, on the bottom, you can see the different wavelengths of light. And on the y-axis, you see how much each of the colors actually is absorbed from the dyes. So you see the cyan dye as an absorption graph, you see the magenta dye and the yellow dye. So what we basically want is, if you want to make cyan transparent, we need a light source that emits roughly there. So only the cyan goes away, but the magenta and the yellow stays. And then similarly, let's say we want to make the magenta or the yellow transparent, we have to find something that mostly targets. As you can see here, it's not perfect, but close enough. So lucky enough, actually, if you open up a normal office projector that I would normally use to project those slides on, they already have 3 light sources inside, right? They have a red, green, and blue LED, which the projector uses to create the images. So lucky enough for us, if you measure the wavelength of the red LED, it actually is nicely in the position where we needed to deactivate the cyan. The green LED is roughly in the right position to deactivate the magenta, and then the blue LED is roughly in the right position to deactivate the yellow. So what we basically just have to do is, what you saw in those videos, we have to compute how long at each pixel do we have to shine red light, green light, and blue light to go from black to our desired target color of the photochromic dye. So there's obviously like algorithm behind this that optimizes on how long we have to shine the color at each pixel, but I can tell you more about this later. Okay. So for the algorithm, I just want to briefly summarize this here. You can actually see that we first had to collect some data on how does red, green, and blue light impact the different dyes. So if you actually look at the first chart, you can see if you just paint the photochromic dye on a surface and you shine red light on it, the yellow material will still be there, but the cyan and the magenta will, for instance, go away. And you see data collected for green light and also for blue light. So once we had this data collected from our experiments, we simply had to feed this into an optimization algorithm. I will not go into the detail here, but it's basically trying to minimize the error between the color you actually want and the color we realistically can do with our system, because we can't do the full color spectrum. So the material preparation is actually really fun, and that's something you could even do yourself because it's really simple materials. So first we have these photochromic dyes, which are these little bottles at the bottom. It's just like a powder, basically, you can buy from a company. Then for our system, we buy automotive lacquer from a hardware store as like our mixing liquid. And then we just need a really low cost $100 mixer to put everything together. So you can see this here, we put the lacquer and then we put the cyan dye. We mix everything together. We do the same thing for the magenta. And then we mix the same thing for the yellow. And now we have each of the photochromic colors separately. You can see this here, just how they get activated. And then we have to mix them in the right ratio together for our smart programmable material. So for instance, if you do this material mixing yourself and you can get the algorithm from us, you can actually get relatively quickly started just on trying this out with programming the different colors. All you need is another projector and a small UV light for like $100. So what did we achieve with this project? So I showed you this initial vision that I started out, and while obviously we have not fully achieved it, it's not that you can just like click and within 1 second your object is reprogrammed. I would say we actually came a lot closer to this vision of making physical objects appearances as reprogrammable as you would have it in a digital world, right? So I showed you this example here of the car where, you know, within like 20 minutes, you can actually change the color of this object here. So one question for me as a researcher is always, what can we now do with this technique now that we have it developed? Are there any follow-up research opportunities? So one thing I'm super excited about is just to see like how fast can we actually go? Because right now, as you saw, it takes 20 to 40 minutes roughly to program a surface. But we already found that if we double the light intensity, we can roughly double the time speed up. So you can see if you use 2 UV lights versus 1, you can be twice as fast. So one question I have is like, how fast can we get? Can we maybe get to like the 1-click, 2-second approach? That's something we are exploring right now. We also evaluated not just using a UV light, which is just a light bulb, but actually using a UV projector that can program each pixel individually with the UV light. And we were able to do these grayscale preview textures here within just 60 seconds. So again, in the interest of doing something like super quickly, I think this is really getting into the right direction of seeing something maybe even in real time in the future. This is something I'm also super excited about. On the left side, you can actually see our current system. You see the little projector there, you see the little UV light, and you see in the dotted outline the object on the platform. So the system served us well for the initial exploration, but imagine if you wanted to reprogram clothing, you really don't want to stand in front of the projector and, like turn around. That would be super hard and really impractical. So we're actually checking right now, can we get rid of the whole projector system? And instead, maybe integrate the light source directly with the object. So in the middle, you see a new collaboration we are working on where we have a fiber that you can actually weave into clothing. And the fiber has small, super tiny LEDs already integrated, which are RGB and UV. And they have the same capabilities as the UV light source and the projector. So in the future, we may be able to have this standalone fiber that we can simply weave into clothing, and you don't need the projector system at all anymore, and your clothing can just change the appearance, which would be super cool. And then we have also been working on developing the first multicolor printer that uses resins in a tank. So if you're interested in this, I'm happy to tell you more about it. The idea here is to pour the photochromic dyes into the resin tank, mix the resin, and then program the colors during the printing process. Okay, so I told you about programmable appearance, but obviously appearance is not the only thing that we need to really make our objects more like programmable matter that can, react to user input and do other things for the user. So I talked about appearance. The next thing I want to show you is how can we integrate sensing into our environment. So for this, I will talk about a project called Sprayable User Interfaces. Again, if you're interested, you can find it on our website. So here we are spraying conductive ink using an airbrush onto a wall. And then by spraying these conductive inks onto a wall, we can actually make large-scale user interfaces that directly integrate with the environment around us. So here you see one example where we sprayed a display for turning on and off this RGB lamp, maybe because it's dark. And then we sprayed two sliders where you can set the brightness of the light. And you can also set, for instance, the color in the room, simply by interacting with this wall-sized user interface. So the material we used here for spraying is a copper ink, and it's really great because you can use it to make touch buttons. If you make some smart layouts, you can use the same ink for making sliders and dials. You can use it for wires and also to connect your microcontroller. But what is not so great about the copper ink is that you really see it if you spray it on the wall, right? So what we did is we sprayed some nice decorative visual inks on top just to cover it up. What is really cool is there's also a material that is conductive but is transparent. So now what you can do with this is, for instance, spray it directly on, let's say, a piece of furniture like this couch here. So you see my postdoc Michael is spraying some touch and hover buttons here directly on the armrest. And the underlying thing you see here are some projected stencils, so you actually know where to spray as the user. So you can see now this is conductive. And because this is conductive, oops. Awesome, here we go. And because this is conductive, we now have this user interface on the couch. You can actually not see it because it's transparent. But you can now interact and say, let's say, for instance, swipe left, swipe right, to interact with this photo album here on the computer. And because we also sprayed sensors on the backrest, we can even detect that Jason, in this case here, is actually sitting on the couch and in which position. So I was like super impressed by this when I first saw it, because this was one example we created like super last minute before the Kai deadline. And I saw the couch there and I was like, Michael, are you done with this? It's getting really tight. And he's like, what are you talking about? I'm already done with it. Don't you see it? And I was like, no, I don't see it. And I think this is really showing how nicely here the user interface integrates with the physical object without changing any of the base characteristics of this object. Very typical for our work is to always provide also a 3D editor support tool for the user. So here for the couch, for instance, the user can plan the sensor layout, can plan where the microcontroller has to go and the wires. And then we automatically create some stencils for the user to easily create this on the physical object. So we also conducted a technical evaluation, so you can see how well does the spraying actually work on different, let's say, architectural elements, let's say like porous stone or other wall elements. And you can see it actually works pretty well with low resistance on all these different surface materials. I wanted to show this additional example here. This is actually a music interface we now have in my lab space. So this is a column in our lab, and Michael sprayed here this UI on the wall where if you touch one of the notes, you can actually play a song in our lab space as a like interactive music application. Okay. Okay, great. So I showed you how to create programmable appearance and to add sensing to physical objects. What is very important for all of this work is to have editing environments that support the designer in creating those physical objects. So in the next part of my talk, I want to show you a bit more about editing environments that really merge the physical world with the digital world to give you a good preview of what you're actually making. So I'm sure many of you know the concept of WYSIWYG, like what you see is what you get. In fabrication, unfortunately, that concept doesn't really exist yet. So WYSIWYG really enabled a lot of people to participate in computing. And my personal hope is that if we have something like WYSIFAG, like what you see is what you fabricate, we may also be able to get more people to participate in fabrication. So let's look at how this currently looks in fabrication. Let's say you want to laser cut this object here. You actually first, for instance, design an object for laser cutting in a 3D editor, and then you export your design, and then you would go to the material storage, and then you would notice like, oops, I actually don't have enough material for this object. So there's literally like no preview of fabrication constraints whatsoever in the editing tools we have to prepare designs for fabrication at the moment. So there's definitely information missing. So here's one of the projects we developed to help people in that space. So what you can see here is that this is a normal design environment for making 2D designs. In this case here, it's Adobe Illustrator. But we brought some of the fabrication information actually into this editing tool. So on the left side, you see we have a new kind of like materials bar, which on a very basic level is just a set of like fill colors, red, green, blue, and so on, that have an assigned material type. So now when you draw something, you actually directly assign a material. Say, I want to make this from 2mm green acrylic, or I want to make this from cardboard. And then on the right side, we have an overview of all of your sheets that you have in your workshop. And whenever you draw something in a specific material, we pack that part in real time onto the sheet. So you can see this in a video as well. As you can see here, Tisha, one of my PhD students who's the lead of this project, is drawing these circles for the tree. And as she's drawing them, they automatically get packed onto the design. So here in this example, she just duplicated the main tree stem, and it doesn't fit onto the material sheet anymore. So she actually retrieves a warning, and she has multiple options now. She could either decide to try a different material, and our software will say, hey, you have these materials, they are the most similar in color or in thickness. Or she could alternatively also just like downscale the design until it fits. So I showed you this as one example of how, by bringing in a bit more fabrication information, we can actually help the user make smarter decisions already during the design phase. And there are a lot more issues that have like similar story attached to it. And I will show you like one more in the interest of time. So for instance, let's say if you want to make a really nice phone case with a nice customized engraving. Right now, if you make your design for laser cutting, and then you want to make it, it's actually really unclear like how you should choose your settings for engraving this design onto the object. So for instance, if you just bought this phone case, you probably have no idea what material this actually is, right? Is this like, you know, some silicone, or is this more like acrylic? Is this, it looks like wood, but who knows if that's really wood or just like fake wood? Yeah, so it's really hard for you to choose like which power or speed you should use to engrave this. And you probably really don't want to burn your design by choosing the wrong settings. And then the other issue is your design is just like a single path, and you really don't know where should you split it, right? You see there's a diagonal line, but it's really unclear like which part of the flower is above and below this line. So you don't really know how to align it properly. So a project we did to help people bring this like physical information back to the digital world is a project called SensiCut. So here we created this new sensing system for the laser cutter, which you can just attach to the main laser cutter head. And then you say, please scan my design. And what we are doing here now is like just going over each point in the design, and our system can actually analyze what material is underlaying under each point. And as you can see here, the design is then automatically split, and you can simply execute it. So here in this case, it recognized it was a silicone rubber, and then I think the second one was actually a type of wood. All right, so the way we do this is we actually look at the structure of the material. We do not look at the color of the material. Because as you can see in this like column here with the different white materials, there are a lot of materials that just look the same to the human eye, and that would look exactly the same to a camera. So for instance, if you have like cast acrylic or Delrin, Lexan paper, like it's all very white, right? So it wouldn't be visually distinguishable. However, with our sensing technique, where we look at structure via something that's called speckle sensing, we can actually see the different material types. So you just need a laser, a visible laser pointer, and then the light reflects off the surface and results in these so-called speckle patterns. And as you can see in the middle row of these images from the electron microscope that we took, each material has a different surface structure. So it's very easy based from the speckle pattern to differentiate them. So here you see the system in action at one more example, just showing you how like different white materials here can be distinguished. So the user, you know, is not accidentally putting the laser cutter on fire. And most importantly, as you will see on the last example, there are also materials that are just toxic. Yeah, so the last one here, Lexan, that should definitely not be laser cut. And if you are a novice user, you may just not know, right? And then you laser cut it, and then you develop some lung problems. And I think you all agree, nobody really wants that. Okay, super. So I showed you those for like passive fabrication tools, but the same issues also exist for electronic design tools. Just want to show you one more example that we did in the space called Morph Sensor. And here the problem really is that normally you would design your 3D model in one tool, and then you would do your electronic design in some other tool, and there's really no single tool that brings you everything together and gives you the fabrication file at the end for all of these parts of your product. So what we developed here is this new integrated editing environment where you can load electronic components, for instance, from like SparkFun or Adafruit, and then you can drag all of these small electronic components from their modules and put them right on your 3D prototype. Since we start with pre-existing modules, we already know how everything is connected. So you can see here the logic lines are all preserved. And then all you really have to do is just to decide on how you want to lay out those wires. So here we are drawing like the different silver lines. And then you can happily sketch your design right on the prototype. And in the end, we give you a fabrication file you can make on a simple inkjet printer. All right, so you can see the export here. So we are selecting our design and say we want to export this now. We get this unrolled circuit board. And then this unrolled circuit board, we can silver inkjet print. That's a technology where you load some silver ink into a normal printer and you make a circuit. And then based on that, we can use like a simple assembly process to put the electronic components onto the circuit and then put the entire circuit onto the object. So here, Juni, my PhD student behind the project, he's happily soldering on these components. This is a special tape called Z-tape that is used to simply tape electronic components onto a circuit while ensuring there is electric conductivity. And then once he taped on all of the different components, his prototype is basically ready. All right, cutting it out. Okay, awesome. Great. So we did a bunch of different like morphed prototypes to just show that this concept holds across a wide variety of different object form factors. So that's, I think, like a great way to see how the fabrication knowledge can come into a 3D editing environment. All right, so I showed you appearance, I showed you sensing and how we can bring digital and physical closer together also during the editing. And the final thing, the final project thread I want to show you is how we can actually make like fully functional objects just by pushing a single button. Yeah. So I think what I learned over the last years is that not everybody wants to make stuff from scratch. I think that's something that is probably obvious to many people. And for me as a maker, I was always like, everybody wants to make things from scratch, but no, that's not the case. So today, I think it's, you know, we can already download like images, we can download music and we can download video, but we can't really download physical objects, right? So if we download something physical, it's typically just like something passive, like a cup or a cute figure, but it's not something that is fully functional. It's not that you can just download a new phone and have it made at home. So we were actually interested to see, can we make fully functional devices with a simple button click? So to do this, we augmented an existing laser cutter with functionality to make circuits into assembled components. And I'm going to show you how we make this fully functional quadcopter here. So this is a very close-up view of our augmented laser cutter head. So you see the laser cutter is currently cutting the geometry. And then this is our silver head extension. So we can lay down silver traces. You can also pick and place components using a little suction head on the laser cutter as well. So here we are just picking up some of the rotors from the quadcopter and the main microcontroller board. And then we still have to sinter the ink and solder the components. So if you just deposit the silver ink, it's not yet conductive. So we use the heat of the laser here and do another pass, and you can see how the silver traces here are now actually cured. And now we have a fully functional device. So as you will see here, the LED comes on the microcontroller because it's completely working. And then in a second, you will actually see how the rotors start to rotate and the quadcopter can actually fly right off the platform. Whoop, here it goes. All right, these are just like a few additional videos to show you that we can do the traces pretty high resolution if we also engrave like a little throw underneath it. We can also place a bunch of different components really quickly of different sizes, just to show you the different capabilities of the system. Okay, let me wrap up my talk. So today I showed you, or I discussed like how computing has actually revolutionized how we process and interact with digital data today. And I explained a bit how these capabilities are not yet available for physical matter. And what I hope I was able to show you today is that we're actually inching closer and closer towards this vision of having the physical world be a bit more malleable and integrated with the digital world. So I showed you examples from programmable appearance. I showed you how to integrate sensing with objects. I showed you how we can bring physical knowledge into our digital editing tools. And then also how we can just like make physical things at the push of a button by simply downloading a file and saying, please make this for me. And it's ready to fly off the platform in this case, for instance. So with this, I want to thank my super awesome team. They are really the masters behind each project. So please send them an email if you really like the project. It always helps to stay motivated during the PhD journey. I'm sure you all know about this. And then I also want to thank all of our sponsors who supported our research. So with this, I want to wrap up my talk. And if you have any questions, I'm happy to take them.
Excellent. Thank you so much, Stefanie. There was one question on the chat. Actually, there were two questions, but the first question I think you answered already. So is the photochromic